On to part 3 of our analysis of the Michelson-Morley experiment. Remember, we did the headwind-tailwind case using the airplane example and found that the time, round-trip time, was of this form here, 2d over v sub p, where v sub p is the plane, and then times a 1 over 1 minus vw squared vp squared factor, where vw is the velocity of the wind there. So now let's do not same situation, but the plane situation, but with a crosswind this time. So instead of going up and down, the wind's still coming down here, or cross, and we're going from A to B with our plane. So velocity of the plane from A to B, and then back again, distance d again. We want to analyze what is the time that it takes to get there. And to understand this situation, we're actually going to use another analogy that's maybe even more intuitive for us, just to see what's going to happen here with the plane. And then, of course, whatever we analyze here will apply to the situation of a light beam traveling through the supposed ether, because it's just a wave traveling through a medium. And if the medium is moving, if we've got that either wind or either breeze going, whether it's headwind, tailwind type of either breeze to the light beam or a crosswind to the light beam, so the light beam's here, maybe the ether is coming this way, depending on how we're moving or whatever, then the analysis is still going to apply. So, velocity of the plane here going back and forth, crosswind. What's the analogy we want to use here, just to a more intuitive idea of this? And that is, think about swimming across a river. Okay, so if you've got, here is the river. There's the current flowing in the river, and let's say I'm at point A here, and I want to swim directly across to point B, and we'll say there's a distance d, but from A to B directly across. Well, we know that if I were to swim straight like that, the current of the water is going to push me downstream. So if I try to travel straight across, I'm actually going to end up going like that, and I will not end up at point B. I'll end up someplace downstream. Okay? So if I actually want to end up at point B, what I have to do is swim up like this in that direction, and then the current will be pushing me down. In fact, it will push me down that much right there. Assume I've more or less drawn the arrows the same there. And for those of you who know the fancy word for this is a little bit of vector analysis, but you just add the arrows together, head to tail. So here's one arrow. That's my actual velocity here going across, and the river is pushing me down with this velocity here, and therefore my resultant motion through the water, which is what I'm interested in, is going to be straight across, more or less there, and so I'm going to get to point B instead of ending up downstream. So I have to swim essentially partly upstream so the current carries me downstream, so I end up at B here. And that's exactly what the analysis is here with the plane, is that instead of the water current here, it's the wind that's pushing the plane off course, so that if it tried to just go straight across in a straight heading from A to B, it'd end up off course down here. So instead it has to head into the wind at a certain angle, which we don't have to worry about, fortunately, but head into the wind at an angle such that it ends up at B where it's supposed to be. And so what are the quantities here? Well, it's flying through the air at velocity v sub p. So that's the actual velocity of the plane through the wind, or if you want the swimmer, the velocity of, maybe we're swimming, velocity of us through the water there. And then the current is v sub w, in our plane example, the velocity of the wind. And so that's going to be this quantity right here, this side. Notice we have a triangle here. And so that's going to be v sub w there. My arrows are a little messy, but if we get, that's the arrow for the wind. That's the arrow for the velocity of the plane. And then what's this arrow here? What's the actual velocity from A to B that we're traveling? We'll just call that v actual. Okay. So if I want to end up at B, I have to point my plane in a direction away from B at a certain angle so that the wind carries me such that I end up at B. But obviously I have to use a little more fuel this way because I'm traveling actually a farther distance there. In a sense, I have to have a higher velocity to end up over b with a velocity v actual. So what is v actual? We know what v sub p is, the plane. We're assuming we're given that, maybe 300 kilometers an hour, or whatever we have to be using, 500, 600, 700. Vw is the velocity of the wind. We're assuming that's a given. And so what's v actual here? Well, here's something I don't think I included in the math review, but we'll put it in right here. Remember the Pythagorean theorem? I essentially have a right triangle here. I have got something that looks like this. This is a right angle. I've got v actual here, and velocity of the plane there, and the velocity of the wind there. I'm given Vp and Vw. Those are quantities I'm working with here. What is V actual? Because note that that's what I want. V actual here is going to tell me how long it takes to get from A to B and then back again. And note in this case it's nice because it's symmetric. In other words, A to B I've got the crosswind, B to A I've got the same crosswind. So if I do it for one case, A to B, then the other case, B to A, will be exactly the same. So the total time will just be twice the one leg time. And the velocity from A to B here will be V actual. That's the net velocity from A to B straight across there, even though the velocity of the plane has to be up like that because the velocity of the wind, of course, is pushing it down. So what is V actual over here? Well, Pythagorean theorem tells me that this squared plus this squared equals this squared. Remember? So if I want this, I can write V actual squared equals the hypotenuse here squared Vp squared minus Vw squared, or more precisely, if I just want to do V actual equals the square root of Vp squared minus Vw squared, assuming that we're dealing with positive quantities here for the velocity, of course. Okay, so that gives me the net velocity of the plane from A to B, or the swimmer from A to B, if you want to think about a swimmer. And so, therefore, I can do the time now. So let's we'll erase our river here, or the plane situation like that. We know what V actual is now. We just found that out. So what's the time? So let's just go, first of all, A to B. The A to B travel time is going to be the distance. Right? So time taken is going to be the distance simply divided by the velocity, the net velocity in this case, which is V actual. And V actual, we just discovered, was square root of Vp squared minus Vw squared. So this becomes d divided by square root of Vp squared minus Vw squared. And that's from A to B. From B to A is exactly the same analysis because we still have a crosswind. So, and it's at the same orientation, so nothing really is different. It's just the other side of the plane in this case, but you still have to arrow up into the wind. And so we can say A to B and then B to A is just going to be that again, so I get twice that for the total time. So we'll say, squeeze this in here, total time is going to be 2d times that. Okay? Now we're going to rewrite it one more thing here, one more time here, one more step. So let's do our little mathematical technique here. And we're going to factor out a Vp squared from here. And we'll do it step by step so we can see what we're doing. So this equals 2d over the square root of Vp squared times 1 minus Vw squared over Vp squared. That was a little technique, trick we reviewed earlier, reminded earlier in the earlier video clip, part 1 of this. I just factor out a Vp squared from each term. So it's Vp squared times 1, Vp squared times that. So that's equivalent to that. I can then split this into 2 square roots like we did before, square root here, square root here. So this is 2d over the square root of, oops, too much there, square root of Vp squared times the square root of 1 minus Vw squared over Vp squared. And of course, the square root of Vp squared is simply Vp. So this becomes 2d all over Vp. And I've got this other factor here, which I'll write as 1 over the square root of 1 minus Vw squared Vp squared. Okay? See where we got that? So here I had the 2d. This just becomes the Vp. And this second part here, the 1 over this, I just pulled out as a separate term there. Okay? So let's just rewrite that, clean it up a little bit here. So the crosswind case, because that's what we've been working on here, is time equals 2d over Vp times 1 over the square root 1 minus Vw squared over Vp squared. And note something important here, something very interesting. This was the crosswind case. We earlier did the headwind tailwind case. They're slightly different. They both have the 2d over Vp factor in there. But note, in this case, it's 1 over 1 minus Vw squared over Vp squared. Here, same thing, but the square root. Slightly different. So in part 4 of this, we'll see how we put this together and how Michelson-Morley put this together and see how it applies actually to the luminiferous ether and light waves traveling through that and how they did their experiment and what the result was of that experiment.